All right, today we are diving into one of the most elegant and honestly surprising ideas in all of math, complex integration. It's a journey that takes a concept you probably already know and just launches it into a whole new, beautiful dimension.
So you definitely remember from calculus that an integral is basically just finding the area under a curve on a plain old x-axis. Simple enough. But what happens when our path isn't a straight line? What if it's a winding, looping journey through the two-dimensional complex plane? Well, the rules change completely, and the results, they are just incredible.
So this right here is the fundamental leap we're making. We're going from a pretty straightforward one-dimensional problem about area to a two-dimensional one about summing up values along some curve. And to even do that, we got to have a new way of thinking about what an integral even is.
Okay, first things first, what are we actually calculating when we talk about a complex integral? Let's break it down.
I know. You see this, and it looks a little intimidating, right? But I promise you, behind all those symbols, it's describing a really simple and intuitive process. Let's just walk through what it actually means.
And this is basically it. You take your path C, you slice it up into a ton of tiny pieces, which we call delta z. Then, for each little piece, you find the value of your function there and multiply it by that piece's length and its direction. Then, you just add them all up. That's it. That's the whole idea of a complex integral.
So that's the process, right? You chop up a path, you multiply, you add. You'd expect to get some unique, complicated number for every single path you draw. But now we get to the first mind-blowing result, a rule that seems almost too simple to be true.
This rule is called the Cauchy-Riemann theorem, and it is an absolute cornerstone of complex analysis. It tells us something really profound about what happens when you just take a simple round trip.
Yep, you are seeing that correctly. For a huge number of functions, if you integrate along any path that starts and ends at the same spot, making a closed loop, the answer is just 0. All that work of chopping up the path, multiplying, adding, it all just perfectly cancels out to nothing.
Now, of course, this magic 0 doesn't work for absolutely everything. There are two really crucial conditions. First, your function has to be analytic inside the loop. Just think of this as being perfectly smooth and well-behaved. No sharp corners, no sudden jumps, nothing weird. Second, the path has to be in what's called a simply connected domain. That's just a fancy way of saying the region has no holes in it. It's like a solid piece of paper, not a donut. Any loop you draw can be shrunk down to a single point without getting snagged on anything.
So this zero theorem isn't just a neat party trick, it actually has this powerful consequence that gives us an incredible amount of freedom, and that brings us to our next really big idea. It's a totally fair question, right? Why should we care that a round-trip integral is 0? What does that actually let us do?
The answer is path independence. This means that for all these well-behaved functions, the specific path you take between 2 points, it just doesn't matter at all. Only the start and end points do. And here's why this works. Imagine going from point Z1 to Z2 along some path. Let's call it C1. Then you come back to Z1 but along a different path, C2, just going in reverse. You've just made a closed loop. And according to Cauchy's theorem, we know the total integral for that loop is 0. Well, the only way for that to be true is if the journey out along C1 was perfectly canceled out by the journey back along C2. And that means the integral along C1 has to be the exact same as the integral along C2. The path is totally irrelevant.
But what happens when those conditions we talked about aren't met? What happens when there is a hole in our domain? This is where things get really fun.
See, remember, that 0 theorem only works if the function is well-behaved everywhere inside our loop. So what happens if there's a trouble spot? A point where the function just blows up or completely misbehaves?
These trouble spots have a name. They're called singularities. They are points where the function basically goes haywire. Think dividing by 0. And these points are the exceptions to the 0 rule, and they are what give complex integration its true power. The integral is no longer 0, and the new answer tells us something incredibly important.
The most classic example, the poster child for this, is the function 1 over z. It's perfectly well behaved everywhere, except at z equals 0, where you'd be dividing by 0. So what's the integral of this function if we take a loop around that singularity at the origin? It's 2 pi I, not 0. It's this specific, fundamental, and just beautiful complex number.
And what's crazy is it doesn't matter how big or small or weirdly shaped your loop is, as long as it goes around the origin just once, the answer is always 2 pi I. And get this, look how specific this result is. If we integrate 1 over z minus z naught raised to any other integer power, like squared or cubed or to the 4th power, the integral around that singularity is 0 again. It's only that simple power of 1 that gives us this special 2 pi I result. It's completely unique.
And this, right here, this is the ultimate takeaway. A complex integral is like a kind of detector. Its value is a message about what's hiding inside the path. A 0 tells you, hey, everything's cool in here, all well behaved. But a non-zero answer, like 2 pi I, it's screaming that there's a special kind of troublemaker, a singularity, inside. This matters hugely in physics and engineering. These singularities can represent things like an electric charge or a vortex in a fluid. The integral is basically measuring the total strength of whatever your path encloses.
So we've seen that if a function is analytic, its loop integral is 0. But as we just saw with things like 1 over z squared, you can have a singularity, a lack of analyticity, and the integral can still be 0. This quote from our source material kind of hints at a much deeper story, reminding us that in math, the exceptions to the rules, well, that's often where the most powerful and interesting ideas are hiding.